Okay, to start us off today, I wanted to cover this. This is actually finishing up one of the sections here that we started talking about already. And so, but what it is, the question is, L1 and L2, are they parallel, intersecting, or skew? Because we know parallel, we know intersecting, that makes sense. When we go to 3 dimensions, though, we can have lines that aren't parallel necessarily, but they don't intersect either. Because let's say we've got a line here, and of course, parallel line would have to be either out from it, below it, around it. So we've got in 3 dimensions, we know about parallel, and then of course intersecting, that. But skew means, well, what if I had a line that's going straight into the board here, through the wall and so forth? That is not parallel to it, and so that's what we mean by skew, in that they don't intersect, but they're not parallel either. They still don't intersect, but so there's 2 things that could happen if lines don't intersect now that we're in 3 dimensions. Another good example of skew lines is if you think about the corner, along a wall. Say I do a line along the base of the wall here. Well, if you go to the top of the wall there and draw a line through that, those lines never intersect. They're kind of perpendicular, but they're not going to intersect, the one along the floor and the one along the top of the ceiling there on the opposite wall. So anyway, just to give you an example of skew lines. So anyway, how do we do this? Well, we know that parallel lines, we've talked about those already here in 3 dimensions. It's that their vectors are parallel, which means what? If one's a scalar multiple of the other, right? So this one, we've got our direction vector. So if that direction vector and then the second one's direction vector is somehow a scalar multiple of the other, or they're proportional to one another. One's a multiple of the other. All right? And so that's easy to check. For this, then, what is our directional vector? Well, when we've got it in XYZ format there, our A, B, and C, doesn't that define the vector? So it'd be 1, -8, and -3 when it's in this parametric equation form. Now, did line 2 purposely different? Because remember that we talked about that's the symmetric form of a line, and they're nice about it in that they do give you, remember, so that's V1. So V2, the direction vector here, remember where the ABC is on it? Yeah, this is A, this is B, and this is C, yeah, in the denominators. So we got -1, -2, and -2 would be the direction vector of it. And we can clearly see that one is not a multiple of the other. That would be 4 times it, but clearly those aren't 4 times there, so they're different scales there. All right, so it's not parallel. Okay, and the way we're going to do it then is we've checked off that it's not parallel. The next thing we're going to try to check then is whether or not it's intersecting. And if you think about it, it's they intersect if they have a common point. There's a common XYZ that works in both line 1 and line 2. So if they have a common XYZ point, so there's an X value and a Y value and a Z value that works in ordered triple there, if you will, that works in all three. Well, we can find this by doing just a little solving of a system. Let's reformat here. The other way they'll list line 2 is they'll do it, instead of using T, they'll use S, so we can make a distinction between these two lines. And remember, on this, it's basically that the parameter, all three of these are equal to the parameter. And so let's call the parameter, instead of T, they'll call it S. So S equals X minus 5 over negative 1. And S equals Y minus 2 over negative 2, and so forth. And what that does is that allows us to get, if S equals that, then what does X equal? So it'd be negative S equals X minus 5. So wouldn't X equal, 5 minus S? And let's see, this would be minus 2S equals Y minus 2. So Y would be negative 2S plus 2, or 2 minus 2S. And then Z, so S would equal Z minus 5 over negative 2. No, here's what we're going to do. So what is this one? Negative 2S equals Z minus 5. And so we got minus 2S plus 5 equals Z. Okay, so here's our X, Y, and Z equation for line 2. All right, so for these to intersect, they have to have a common X and Y. In other words, this X equals that X. At the same time, that Y equals that Y. At the same time, that Z equals that Z. And so that just sets up a three equation system. If we set the X's equal, so we've got 2 plus T equals 5 minus S. We've got negative 2S plus 2, or let's do it 6 minus 8T equals negative 2S plus 2. And we've got the Z's equal, so it'd be 4 minus 3T equals the negative 2S plus 5. Okay, and so there should be a common ST value, which leads us to a common XYZ value, if this is going to intersect. Okay, and so really just go kind of two at a time. I think it doesn't really matter. Doesn't really matter if I look at 2 plus T equals 5 minus S, and 6 minus 8T equals negative 2S plus 2. Solve that however you want to. Multiply by 8 or something like that. So it'd be 16 plus 8T equals 40 minus 8S. And that'll eliminate the T. So that'd be 22 equals what? Negative 10S plus 42. And so it looks like my S is 2. Yeah. So S is 2, which means 2 plus T equals 5 minus 2. So that would be t equals 1. Is that right? 3 minus 2. Now, for this, so that solves these two. But the trick then is, does it work in the other one? Does t equal 1, s equals 2, does that work? Does that work in the third one? Because if it doesn't work in the third one, then they don't intersect. But does it work? Does it work? So it'd be 4 minus 3. Does that indeed equal negative 4 plus 5? 1 equals 1. So that works in all three. So there is a t and an s that works in all three. Now, what that means is these do intersect. Since I've got a common st value that works in all three, there's a common x, y, z. So the x, we've got 2 plus t, y is 6 minus 8t, and we can verify this one this way too. All right, so if we've got, t equals 1, so that would be 3, negative 2, and 1, right? Be our x, y, z. And if we look at the other one, we've got x equals 5 minus s, y equals negative 2s plus 2, and z equals negative 2s plus 5. Is that right? Yeah. All right, so this one we're looking at s equals 2, and so that's 3. Negative 4 plus 2 is negative 2. Negative 2 times 2 plus 5 is 1. So you see you've got 3 to negative 2, 1 for both of them. So they intersect at, these lines here intersect at 3, negative 2, and 1. So that's the way it worked in this one. Now, if they're not parallel, and then we can't find a solution to the system here, then the only other alternative is then that they're skew. So that's the way that works. All right? Is that okay? All right. Something else I was going, oh yeah. There's a problem I was wanting to show you here.
Okay. I remember about their perspective being parallel.
Yes.
I remember that one, that rule, there's also a little bit of magnitude, just cross product, if it equals zero.
Yes.
That makes it
Yes. All right, so this one is back to planes here a little bit. Let's find the equation of the plane. And we've got a point, which is what we need. So through the point 3, negative 6, and 4. But, you know, the other thing we need on a plane is the normal vector, the vector that's orthogonal to it. Well, in this case, they don't give us that. They give us that it's parallel to another plane, x minus 3y plus 2z equals 5. Okay? And so we're finding a plane through the point, but it's parallel to another plane. Well, if you think about this, all right, so let's say we've got a plane here. And it's parallel to this other plane at a little different height, if you will. Well, how are we going to know if those two are parallel? Well, wouldn't it be true, we've got our normal vector here. Let's say it's coming out kind of like that. So that's, well, wouldn't it be true, what about the normal vector over here? What's going to have to be true about those normal vectors? they're going to have to be parallel. Yeah. Yeah, parallel. Yeah. If it's parallel to another plane, then they're normal vectors. So parallel planes, their normal vectors are also parallel. Or the same. We can actually just say, yeah, parallel, and there's scalar multiple, so why not just say we got the same normal vector. Okay. All right, with that in mind then, what is the normal vector for the plane here? Well, remember that a plane, what we have is A, the usual setup, the A, which is the first component of the normal vector, x minus the point, the x value of the point, plus B times y minus y0, plus C times Z minus Z0 equals 0. That's our standard equation of a plane. Well, we don't quite have that format, but if we think about it, what is the A, B, and C of this one going to be for our, because our normal vector here is ABC. Well, if you distribute the A, it's AX minus, so the A is what's times the X, isn't it? What's times the X up here? It's 1. Then the B would be -3, and then the Z would, C would be, what's times is Z? We don't know what the X naught, Y naught, Z naught would be, but we could figure out a point for that, but we just need the normal vector of that. So this is the normal vector of this one, so that's also the normal vector of the plane we want to make. And so we're going to do 1 times X minus, for the new plane we do know a point, X0, Y0, and Z0, so it's X minus 3. And then the B is -3, same as that one. Y minus the Y value, so it'd be plus 6 here. And then C is the same C as that, so Z minus 4 equals 0. And I think this book does go ahead and multiply. Yeah. Something like that. So if we move, really all that changes then from this plane to this one, we have the same ABC. The only thing that changes is the D, if you will. What is this one? -21, -29. So it'll be positive 29 on the other side. Does that sound right? Okay.